All right, hello everyone, and welcome to my channel. And this channel is for educational purposes. We take a look at great theories of everything and things that have probably been suppressed from your understanding or your exposure to them, and do deep dives on them to, give you the full information about how they operate and how they can benefit your life. Today is our 469th video on the reciprocal system of theory from Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates about how he believed the universe operated, and then took those postulates and elaborated them through a process of deduction into a theoretical universe. What his universe would look like if his postulates were correct. And then he compared his findings with the observed and measured findings of the legacy scientists. In books like the one we're looking at today called Basic Properties of Matter. This book is pretty much on chemistry. And in this book, Larson comes up with equations that he derives theoretically for many of the basic properties of matter, like the melting point or the specific heat, compressibility, and so on. And then he compares those with the scientific tables. We yesterday just got started with chapter 8, which is on thermal expansion. So, the general idea is as you heat something up, it expands. But some substances expand more than others. And so there's equations that you have to be able to, account for the different expansion depending upon what substance you have. And Larson kind of shows how he goes about figuring that out. But first, we'll just take a look at Larson's two fundamental postulates. The second postulate really is just for the purposes of deriving those deductive, through the process of deduction and deriving that theoretical universe from the first postulate. So the second postulate just states that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So basically, Larson is saying, I'm using the general method of science in order to derive my theoretical universe from my first postulate. And that first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So Larson was not the first person to ever propose a universe constructed out of motion, as opposed to matter or energy or force. Other people had done that, like Thomas Hobbes and René Descartes. But Larson was kind of the first person to make it work because he took pains to define motion. And Larson defines motion as the relationship between space and time. So for Larson, motion is a fraction, with space or time as the numerator and time or space as the denominator. You can see that in speed. Speed is, the bike is moving 15 miles per hour. 15 miles of space in 1 hour of time. Space over time. But there's a reciprocal relationship there that you can also see. If you decide to double the speed, you can say the bike is now going 30 miles per hour. Or equivalently, you can say the bike is now going 15 miles per half hour. You can either multiply the space or you can divide the time in this case. And so that shows a reciprocal relationship. Now, Larson took, this idea of speed, space over time, but he extrapolated that to all scientific phenomena. There are all forms of motion. Matter is a form of motion. Energy is a form of motion. Acceleration is a form of motion. Force is a form of motion. And all other scientific, units that you can think of are all forms of motion, and they all have their time over space or space over time signatures, such as energy is simply time over space, while force is time over space to the second power, while acceleration is space over time to the second power, and so on. And when Larson speaks of motion, he speaks specifically of a more generalized kind of motion that he calls scalar motion. Scalar motion is something that, again, other scientists have recognized, but they haven't recognized the significance of scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. So you can envision a scalar motion using a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other. They will be moving in every direction. There is no specific direction that they'll be moving. Every dot will be moving away from every other dot. And indeed, every location on that balloon will be moving away from every other location. It's like the balloon itself is stretching or moving. And the dots are just kind of along for the ride. And that is an outward scalar motion. If you reverse, and Larson refers to that as the progression. So this progression is the basic motion of the universe. And it is occurring at all times, in all places. Omnipresent and eternal progression. And this progression is occurring at a rate, which is determined by this discrete unit postulate. Space, time, and motion all come only in discrete units. And the speed of the progression is 1 unit of space in 1 unit of time. Again, space over time equals speed. And the speed of the progression is 1 over 1 equals 1. Larson calls that unit speed. And just like all of the other scientific phenomena, each one of our units comes in units. So there is a unit of speed, there's a unit of matter, there's a unit of acceleration, there's a unit of force. That is the discrete unit postulate. And in this case, 1 unit of space per 1 unit of time is also known as the speed of light. So this is the progression. This is omnipresent and eternal, occurring at all times and all places. Outward motion at the speed of light. Larson refers to that as the progression of the natural reference system. So Larson has a reference system that is moving, a moving reference system. And that's where he makes his measurements from. measures from the location or from the motion of the progression, outward or inward from that progression. And so if something is moving faster than the speed of light, Larson calls that cosmic. It's in the cosmic sector. And if it's moving slower than the speed of light, he refers to that as the material sector. The material sector is really the only sector that scientists know about. The cosmic sector is more or less blasphemy to the modern scientist, being, under the influence of Einstein's dictum that says that the speed of light is the maximum speed of the universe. In Larson's system, the speed of light is the midpoint of the universe. Half the universe is moving faster, that's the cosmic sector, and half is moving slower. Now, another part about the first postulate is that space, time, and motion come in 3 dimensions. And you can see that if you really kind of abstract that progression. If you decide that, let's say that you take that balloon and you suck in the balloon instead of expanding it, instead of exhaling, you inhale, and the balloon contracts, then all the dots will be moving toward each other. And this is what Larson refers to as gravitation. And so all of the dots will be moving toward each other. But there won't be a force field there. There's no, each dot is pursuing its own course. But it looks like there's a force field. You can see that if you take one of the dots and you arbitrarily say this dot is motionless, then it will appear as if all of the other dots are moving toward that first dot, that there is a force of attraction between your dot and every other dot. But that is not the case. All of them are just moving under their own auspices. All of them are maintaining their place on the surface of that balloon. And so that is what Larson calls an as-if force. And that kind of shows you how you can basically stop the universe and make an abstraction. And that's what happens with the 3-dimensionality of space. Generally, when we, a couple of the obstacles that make it difficult to get with the universe of motion is first that you have to be able to imagine motion without anything moving. That progression of the natural reference system, that occurs in an empty universe. That occurs before there is anything. Motion comes before anything moving. And you have to accept that if you're going to accept a universe of motion. And then for thousands of years, we've thought of space and time as being basically the container of the universe. That space is this 3-dimensional thing in a still frame that we move through, or we see a forward and backward and front, side to side and up and down. And then we see ourselves at the events as unfolding in time. So this is the container viewpoint. The space and time is kind of like the stage on which we go through our drama. But in Larson's universe, space and time are the contents of the universe. The universe is made out of motion, and motion is made out of space and time. Space and time have no independent existence. They only exist together in motion. And so But when we kind of slack off on that understanding, and we revert to this idea of the container universe, then we revert to what Larson calls the stationary spatial reference system. We see coordinate space, 3 dimensions of space, in progressing time. Time is always moving forward, getting later and later and later, and in a scalar manner, not in any specific direction. Okay, so that's what we've done is, because of gravity, we've stopped the universe, and we've abstracted space to be this 3-dimensional still frame, but time is still flowing in a scalar manner. So that spatial reference system is really an artifact of the material sector. We are grounded in a spatial reference system. But by the reciprocal postulate, there is also a location in the universe where there is coordinate time, 3 dimensions of time in a still frame, and progressing space, where space is progressing. Space is always getting farther and farther and farther apart. And Larson refers to that as the temporal reference system, and that occurs in the cosmic sector. So you can see the reciprocity between the material and cosmic sectors. When you cross that speed of light boundary, you have to interchange the roles of space and time. You go from coordinate space and clock time to coordinate time and clock space. Now, there is also a subregion within both the material sector and the cosmic sector where you have the discrete unit postulate in terms of space and time, less than 1 unit of space and less than 1 unit of time. In the material sector, you have a unit of space, and when 2 particles or atoms or molecules approach each other to 1 unit of space apart, which is approximately 2 millionths of an inch, then they can't approach each other any closer, because that is the minimum. You have to have a full unit before you have anything. And so if you don't have a full unit, you don't have anything. So they cannot approach each other any closer than that 1 unit. What they do instead is they move further apart in time. And by the reciprocal postulate, less time equals more space, less space equals more time. And so more time equals less space. And so it appears as if they continue to move closer together in space, but what they're actually doing is they're moving in time. But we see it in space because we only see space because we are anchored to a spatial reference system. So Larson refers to this as equivalent space. It's not really happening in space, it's happening in time, but we see it in space. And the same thing happens in the cosmic sector, except with time and space interchanged. When they approach each other to 1 unit of time, which is 1.52 times 10 to the minus 16 seconds, then they can't move any closer in time, and they move further apart in space. And also, so Larson refers to these as the time region in the material sector and the space region in the cosmic sector. If you don't have a full unit of space, then you only have time. And if you don't have a full unit of time, then you only have space. And when you cross that boundary, again, the rules invert, and now the progression is inward in equivalent space, and gravity is outward in equivalent space or time. Now, the question is, the progression of the natural reference system is the source of everything. How do we harness that source and create, matter and aggregates of matter and everything in the universe? And that's done by reversing the progression and turning it into gravitation, turning that outward motion of the balloon into an inward motion. And this is done to start with photons, vibratory units, and then the vibratory units need to be rotated back because, again, the progression is in 3 dimensions. So you can't just rotate it in 1 dimension. It has to be rotated back in all 3 dimensions. And so in Larson's periodic table, he has every atom has 3 numbers. The first 2, A and B, are 2-dimensional rotations, and the third number is a 1-dimensional oppositely directed rotation. And so those are what are needed basically to roll back that progression, the source, to gravity, which is atoms and molecules and aggregates of matter. And so those are the 3 numbers that Larson uses to derive his equations for the basic properties of matter. So we're going to take over here in Chapter 8 on thermal expansion. Larson just got done going over Charles's law, which is a alteration of Boyle's law. Volume equals a constant times the temperature at constant pressure. So Boyle's law, I believe, is PV equals RT. Pressure times volume equals temperature times a constant. But then when you have constant pressure, then you can get rid of the P part, and V equals KT, constant times T. And we'll start right here. The relation E equals PV, energy equals pressure times volume, is merely a restatement of the definition of pressure in a different form, and is therefore valid in the time region inside unit distance, as well as in the ideal gas state. Now, the time region is for solids in 3 dimensions, liquids in 2 dimensions, and I guess it would be vapor in 1 dimension, and a gas is completely outside of the time region and is in what Larson calls the time-space region, which is the rest of the material sector. Since, and in the time region, an equivalent space is a second power region. When we look across into the time region, we lose something in the translation. Larson refers to that as the interregional ratio. We can't see everything that's going on in the time region. And also, in equivalent space, what we see is a second power relation. So all of Larson's equations have to be adjusted accordingly. So he's doing that right here in the time region, even though in the time-space region, or in the material sector, the relation is E equals PV, or E equals KT. V equals KT. In the time region, that equation, I don't know how he got from E equals, that's what he has written, E equals KT squared. I guess PV equals T. So E equals KT squared. In the time region, it follows that in this region, PV equals KT squared. At constant pressure, this reduces to V equals KT squared. Okay, so normally V equals KT, but in the time region, it is V equals KT squared because equivalent space is a second power relation. Now, Larson probably explained that like 6 chapters ago, but he would have probably done well to restate the reason why he was doing that. But that is the reason why he's doing that, because equivalent space is a second power relation. In our consideration of volume changes in solid structures due to the addition of thermal energy, we will usually be interested mainly in the coefficient of thermal expansion, or derivative of volume with respect to temperature. Now, Larson does this in practically every chapter. In a universe of motion, Larson tends to be more focused on rates of things. That's why he looks at specific heat. It's the rate of heating something up, or specific rotation. And in this case, we will usually be interested mainly in the coefficient of thermal expansion, or the derivative of volume with respect to temperature. So what he ends up doing is using calculus and integrating to figure out the rate of thermal expansion. We're not just concerned with the expansion itself, but with the rate of it. And this is obtained by differentiating equation 6.3, which was the V equals kT squared. So by differentiating, then you end up with the rate of volume per time equals 2 kT. And again, Larson does this every chapter, but he kind of, Larson is writing for a scientific audience, so he just assumes that everybody has got great facility with algebra and even up to calculus. And so he tends to, I had to study this stuff to understand the various steps that he goes through, because he doesn't explain the steps that he goes through when he arrives at these equations. And that makes it very difficult to follow. But again, Larson was writing for an audience where he just assumed that you already knew this. Unfortunately, that very same audience is absolutely not receptive to any type of new ideas, as far as they already think they know it all. And so the audience that Larson should have been trying to reach is the audience that he would have needed to explain this stuff to. So there's a disconnect in Larson's writing between his most fertile audience and the audience that he's writing to are not the same people. Okay, aside from the numerical constant K, this equation is identical with the specific heat equation, where the value of N in that equation is unity, where there is a close association between thermal expansion and specific heat up to the first transition temperature defined in Chapter 5. For all of the elements on which sufficient data are available to enable locating the transition point, this transition temperature is the same for thermal expansion as it is for specific heat. Each element has a negative initial level of the expansion coefficient, which he explained way back in probably chapter 4 or 5, that is related to the 2 photons that are at the core of every atom. And so this number is -2/9 in most cases and -1/9 in some. Each element has a negative initial level of the expansion coefficient, the magnitude of which has the same relation to the magnitude of at the transition point as in specific heat, that is 2/9 in most cases and 1/9 in some of the electronegative elements. Now this transition point is a point at which the atom changes from basically from its first rotation to its second rotation, remembering that an atom has 3 different levels of rotation, and those are quantized, but they can be up to up to 5, really. And so when it switches from rotation 1 to rotation 2, the slope of the line of the specific heat curve changes. And the atom does that in order to basically stay in the solid state for as long as possible, because the solid state is more probable from a probability standpoint than the liquid state. And so that's what basically the whole concept of specific heat is, you know, that the atom is going to do whatever it possibly can do in order to avoid getting to the melting point. And here with thermal expansion, it looks like the atom is ready to do a lot of those same things because the equation is the same. At least, he says, up to the first transition point. We'll see what happens then after this transition point. Okay, it follows that if the coefficient of expansion at the transition point is equated to the 4.63 specific heat, which is the quantized temperature, the first segment of the expansion curve is identical with the first segment of the specific heat curve. Beyond the transition point, the thermal expansion curve follows a course quite different from that of the specific heat because of the difference in the nature of the two phenomena. Since the term n to the third power is absent from the thermal expansion equation, the modification of the expansion curve that takes place where motion of single units is succeeded by multi-unit motion involves a change in the coefficient k. The expansion is related to the effective energy, that is, to the temperature, irrespective of the relation between total energy and effective energy that determines the specific heat above the first transition point. The magnitude of the constant k that determines the slope of the upper segment of the expansion curve is determined primarily by the temperature of the endpoint of the solid state. Okay, we're going to leave it there for today. That is a very important paragraph, I believe. That's where he gets into the theoretical difference between, you know, specific heat and thermal expansion, and kind of explains the two factors on what's involved. So we might try to unpack that a little bit tomorrow and then move on and get further along in the chapter. So keep hanging in there. We're making progress, and pick up the breadcrumbs. And thanks for tuning in today.